Why is it that a state-of-the-art AI can write a flawless asynchronous microservice in Python in like 5 seconds, but then confidently tell you that 1,234 times 5,678 is, well, completely wrong?
It's pretty wild to watch, honestly.
Welcome to the deep dive. It's late, the glow of the monitors is basically the only light in the room right now, and we're tearing apart the architecture of large language models to find out why they are so completely blind to basic arithmetic.
Yeah, we're really getting into the intersection of mathematical reasoning, probabilistic text generation, and, well, the fundamental structures of data parsing.
Because it's the ultimate cognitive dissonance in modern software engineering for anyone listening to this. You watch a system architect, a lightweight server, handle complex JSON payloads, navigate API authentication without a hitch, and then...
And then you ask it to do a basic calculus problem.
Exactly, and it spits out an answer that looks incredibly convincing, perfectly formatted, and is just entirely hallucinatory.
I know every engineer listening to this has bumped into this paradox.
Yeah.
You honestly start doubting your own prompts at some point. Like, did I ask it wrong?
Right. But we're going to look under the hood today, moving from the mechanical flaws in the base architecture to the linguistic hacks we use to force accuracy, and finally into a genuinely transformative paradigm where we pair probabilistic AI with deterministic compilers.
Because we really have to start at the root cause. It's not a deficit in the model's neural network parameters. It's an issue with the very first step in the data pipeline.
Which is tokenization, right?
Exactly. We're talking about tokenization, specifically byte pair encoding, or BPE. Tokenization inherently destroys numerical structure.
Wait, destroys it how?
Well, large language models don't process the world in numbers. They process the world in subword tokens that are like optimized for human language compression.
Oh, right. Because byte pair encoding was designed to group common character sequences together. Things like ING or TION become single tokens just to save compute and expand the context window efficiently.
Yeah, exactly.
Yeah.
But applying that linguistic compression strategy to mathematics is, it's a fundamental mismatch.
It's basically catastrophic for mathematics.
It really is. Think about a base 10 numeric system. Positional value is everything. The 4 in 400 carries an entirely different semantic weight than the 4 in 14.
Obviously.
But to the tokenizer, if the sequence 1-4 appears frequently in the training data, say, because of dates or common measurements, it just gets mapped as a single token. Meanwhile, 40 might be a totally separate single token.
Ah, I see. So the neural network isn't seeing a 4 shifted over one decimal place.
No, not at all. It is seeing two completely unrelated vector embeddings in its high-dimensional space.
Wow. That completely severs the geometric relationship of the numbers.
Exactly. If you give the model the integer 1,234, it doesn't allocate memory for numeric type. It doesn't parse it as an integer or a floating point value.
So it's like asking the model to do math where the number 1,000 is treated no differently than the letters in the word cat.
That is a perfect analogy. The tokenizer might chunk 1,234 into the token for 12 and the token for 34. But if you input 12,345, it might chunk it into 1, 23, and 45.
Because the parsing boundaries are totally arbitrary, based on statistical frequency in text, not on mathematical logic.
Right. It's essentially asking the model to do math in an alien alphabet where the letters change their values depending on what other letters are standing next to them.
Man, if the model doesn't even know that the token for 4 represents a value strictly 1 greater than the token for 3, and just maps them as arbitrary coordinates that occasionally appear near each other in Wikipedia articles, no wonder addition fails.
Yeah, the architecture is structurally blinded to arithmetic by the exact mechanism that allows it to generate human language so fluidly.
Because it's an autoregressive engine.
Right. Trying to predict the next token based on statistical probability over a vast training distribution. If it hasn't seen that exact sequence of numbers in that exact arrangement a million times, its statistical prediction is just going to fall flat.
So if the base architecture fundamentally mangles numbers before they even hit the transformer layers, how are we using these models in production today? Because we aren't rewriting the foundational architecture overnight.
No, we definitely aren't. We have to be relying on engineering workarounds.
Right, which means manipulating the context window to artificially constrain the probability space.
Exactly. This is the underlying mechanic of chain of thought prompting.
Ah, the famous think step-by-step prompt.
That's the one.
I do have to push back a little on chain of thought being presented as this brilliant hack, though, because from an engineering standpoint, it feels incredibly fragile.
Oh, it is. It absolutely is.
Right. I mean, wait, so when we ask it to think step by step, it's not actually thinking harder,
Yeah.
right? We're just breaking the calculation into chunks small enough for reliable pattern matching.
That's exactly what we're doing.
Because when we ask it to unroll the calculation, it isn't suddenly firing up a hidden math coprocessor. It's still just predicting the next text token.
Yep, just text prediction.
So if it makes one tiny statistical error on, say, step 4 of a 50-step calculation, the entire downstream context window is poisoned. The attention mechanism will just heavily weight that hallucinated number. How does that actually solve the reliability problem?
Well, you've identified the exact vulnerability of chain of thought. But to understand why it works most of the time, we have to look at how the attention heads operate within the transformer.
Okay, lay it out for me.
When you ask a model to compute 345 times 678 in a single shot, the self-attention mechanism is trying to map the relationships between all those shredded numeric tokens simultaneously just to predict a 4 or 5-digit output sequence.
Right, and the search space for that prediction is massively unbounded.
Exactly. The statistical probability of nailing the exact correct token sequence is near zero.
Because it's trying to make a massive conceptual leap across its vector space.
And this is the hack, when you force it to output step 1, multiply 5 by 8, you are utilizing the scratchpad space of the context window.
So the attention heads are now tightly focused on just the 5 and the 8.
Yes. And the highest probability token to follow that specific, highly constrained linguistic sequence is 40.
Okay, I see. And once that 40 is generated, it becomes part of the immutable prompt for the next step.
Exactly. It's appended to the context. The attention heads now have a solid, factual anchor to calculate step 2.
Wow. So we are bridging the gap between text prediction and mathematical logic by forcing the model to walk down a very narrow, highly predictable path.
Right. It reduces the dimensionality of the prediction. We are treating the symptoms of tokenization by slowing the autoregressive generation down, turning a massive statistical leap into a series of highly probable micro-predictions.
I mean, it's pragmatic, but as an architect, relying on an LLM to reliably chain together 50 micro-predictions without a single hallucination, it feels like relying on a junior developer who just point-blank refuses to write unit tests.
I love that analogy. It's so true. There is a hard ceiling to pattern matching. Eventually, the scratchpad gets too long, the attention mechanism degrades, and it totally loses the plot. We need a better paradigm.
Which is why the industry standard for production systems has moved to tool use.
Exactly. We stopped trying to force a probabilistic text generator to do deterministic arithmetic, and we just give it an API to a dedicated runtime.
We build a microservice architecture. You separate the concerns. The LLM is the systems architect. It handles the semantic reasoning, the interpretation of the messy user prompt, and the overall execution plan.
Right, it maps out the logic.
But when it's time to actually crunch the numbers, it hands off the actual execution to a dedicated compiler or calculator to guarantee precision.
The implementation of this is where it gets really fascinating from an execution standpoint. The model is fine-tuned to recognize when its probabilistic generation is, insufficient for the requested task.
So it knows when it's out of its depth.
Basically, yeah. When it hits that threshold, it generates a specific syntax, say an XML tag like execute Python, followed by a script.
Whoa, so it literally pauses its own generation. The inference engine intercepts that specific string, halts the autoregressive loop, and passes the payload to a sandboxed Python kernel.
Yep. It waits for the execution, captures the standard out, and then injects that precise string back into its own context window.
And then it just closes the XML tag and continues the natural language response as if it had known the answer all along.
It's seamless. It bypasses the tokenization trap entirely because the LLM is no longer trying to predict the mathematical answer. It's just predicting the correct Python syntax to derive the answer.
We are using a probabilistic language engine to command a deterministic machine. That's brilliant. But wait, what happens if the Python script throws an error, like a syntax issue?
See, that's the most powerful part of the loop. If the sandbox kernel throws a syntax error, the runtime feeds the raw stack trace right back into the LLM's context window.
Seriously?
Yeah. The model uses its primary strength parsing complex text to read the stack trace, identify the syntax error in its previous Python script, write a corrected script, and call the tool again.
Oh, wow. It's writing, executing, and debugging its own callbacks in real time. That is robust.
Very robust.
But still, relying on a Python interpreter is fundamentally just slapping a patch on a broken engine. Tool use makes the system usable for a deployed product, but what if we want to actually advance the state of the art?
Right, if we want a foundational model that inherently speaks math, we can't just bolt a calculator onto a generic language model. We have to change the base training entirely.
So we enter the realm of specialized mathematical models. You look at the architecture behind systems like Minerva, Lemma, or DeepSeek-Math from our source material today.
And those models reveal a hard truth about current AI development. When it comes to complex logical domains, brute force scaling has hit a massive wall.
The scaling laws. I mean, for a long time, the prevailing wisdom was that if you just threw more compute and more exabytes of scraped internet data at a larger parameter model, emergent reasoning capabilities would simply materialize.
Yeah, but brute force doesn't work for mathematics. The signal-to-noise ratio on the open internet is entirely too low.
Too much garbage data.
Exactly. To build a model like Lemma, the methodology shifts from scale to extreme data curation. You stop scraping Reddit, and you start feeding the network millions of highly structured, peer-reviewed academic papers from repositories like Arc4.
But wait, earlier we established that tokenizers shred numbers and equations. How do you feed it ArcSef papers without the tokenizer mangling the complex calculus formulas into useless statistical noise?
That's the million-dollar question. The key engineering breakthrough here is preserving the raw LaTeX formatting during the data ingestion pipeline. If you strip the formatting and feed the model plain text math, you lose all the spatial and logical relationships.
Right, because in LaTeX, an equation isn't just a string of adjacent characters. It's a structural graph.
Exactly. When the model parses the LaTeX syntax for a fraction, it learns that the tokens inside the numerator block have a specific functional relationship to the tokens in the denominator block.
Oh, that makes so much sense. It isn't just reading left to right anymore. It's actually mapping the geometric and logical dependencies of the equation right into its vector space.
We are teaching it the grammar of mathematics, not just the vocabulary. By immersing the transformer in high-quality, step-by-step proofs, it starts to internalize the structure of logical deduction.
So its statistical predictions become deeply aligned with mathematical axioms, because that is literally the only language it has ever read.
Yep. It develops an intuition for where a proof should go next, based on the structural weight of the equations it has processed.
That is genuinely reassuring for any listener. It proves that thoughtful engineering, curated data, and clever methodology still trump brute force scaling.
It does. But, and there's a big but, this introduces a new, highly deceptive problem. Because it has specialized entirely in mathematics, it gets incredibly good at mimicking the vibe of complex logic.
Oh, the vibe of logic. Because it's still fundamentally a probabilistic engine predicting the next token.
Exactly. Which means a specialized math LLM can produce a proof that looks flawless, beautifully formatted in LaTeX, densely packed with valid mathematical notation, but containing a subtle, catastrophic logical error hidden on line 42.
Plausible-sounding nonsense scaled up to postgraduate mathematics.
Right. And because the output is so specialized, it becomes incredibly difficult for a human to quickly verify if the model actually solved the problem or just hallucinated a very convincing illusion of a solution.
Which brings us to the bleeding edge, the ultimate synthesis. We've looked at the mechanical parsing flaws, the context window hacks, the tool delegation, and the specialized base models.
But the final paradigm shifts the entire landscape.
We stop trying to make the probabilistic model perfectly accurate, and instead we pair it with a system that is fundamentally incapable of lying.
We combine the large language model with a formal proof assistant.
Yes. For the software engineers listening who work in critical systems, aerospace, cryptography, formal proof assistants, systems like Lean, Coq, or Isabelle.
And these are not probabilistic. They are uncompromising deterministic compilers for logic.
They check mathematical proofs line by line to ensure every single step mathematically derives from fundamental axioms.
They are the absolute antithesis of a neural network. I mean, an LLM guesses, a formal proof assistant verifies. If a proof compiles in Lean, it is indisputably mathematically true. There is no hallucination.
The dynamic between these two systems is just incredible to me. You have the LLM acting as this eccentric, highly creative heuristic search engine.
Yeah, it's like a creative mathematician making wild intuitive leaps.
Exactly. It can look at an unsolved theorem, draw connections across vast, high-dimensional data sets that no human could hold in their head, and hallucinate a potential intuitive path to a solution.
But intuition is messy. So the LLM translates its proposed proof step into the strict, rigid syntax of the Lean compiler. and it executes it.
It submits its creativity to the uncompromising peer reviewer.
That's a great way to put it.
So walk me through the execution loop. What happens when the LLM's intuition is logically flawed?
Well, the formal proof assistant throws a compilation error. But just like with the Python interpreter we discussed earlier, the LLM doesn't just crash.
Let me guess, the error message from Lean is highly specific.
Very specific. It points to the exact logical disconnect. The LLM parses that error trace, updates its context window, adjusts its trajectory away from the flawed logic, and generates the next probabilistic attempt.
Wow, it creates a massive self-correcting loop. The LLM isn't just generating text into void anymore, it has a ground truth environment.
Exactly. It can rapidly traverse thousands of complex logical pathways, and the formal proof assistant acts as the ultimate guardrail. It instantly prunes the branches of the search tree that violate mathematical axioms and allows the valid paths to proceed.
It brings the power of massive pattern recognition to the strict domain of formal logic. The implications of this architecture go far beyond just fixing basic arithmetic.
Oh, absolutely.
Yeah.
We are looking at a system that could eventually discover genuinely new mathematics. It can explore conceptual spaces that are simply too tedious or complex for human mathematicians to traverse manually.
All guided by AI intuition, but constrained by absolute, verifiable truth.
It's the ultimate synthesis of creativity and engineering rigor.
We have covered serious ground tonight. We started way down in the weeds with byte pair encoding, identifying how the very mechanism of text compression structurally blinds these models to numeric values.
And then we examined how manipulating the attention heads via chain of thought provides a fragile workaround, and how offloading execution to Python sandboxes creates a robust microservice-style safety net.
And moving past the patches, we looked at how feeding models structural graphs via latex builds deep mathematical intuition, culminating in this incredible hybrid architecture. The probabilistic neural network dreaming up the proof, and the deterministic Lean compiler verifying it.
From broken parsing to literal mathematical discovery.
Which perfectly sets up where we are heading next, because tomorrow we are leaving the clean, verifiable environment of formal proof assistance entirely.
Oh yeah, tomorrow's going to be fun. We are going to dive into the murkier territory of logical reasoning deduction, induction, and abduction.
That is going to be a heavy one, because once you step outside the realm of strict mathematical axioms and compiled code, the line between a valid logical inference and a highly plausible hallucination gets incredibly blurry.
It really does. How do these architectures handle ambiguity in real-world context when there is no runtime API to check their work?
That is the frontier of cognitive architecture, and that's tomorrow's deep dive.
I can't wait.
I'm already looking forward to it. But before you close your IDEs tonight, I want to leave you with a final thought to mull over. As software engineers, we are used to being the ones who write the logic and verify the execution. But think about this hybrid dynamic we just unpacked. If AI is now capable of providing the creative intuition to traverse massive search spaces and deterministic compilers handle the uncompromising verification, what happens to our role?
Right.
If the machine can dream up the complex architecture and rigorously mathematically verify that it's flawless, perhaps our ultimate role in the future won't be doing the math or even writing the code. Perhaps our only job will simply be deciding which mathematical questions are actually worth asking. Think about that. We'll catch you on the next deep dive.